NDE planning, inspection strategy, and real-world limitations. Module 2. Gary A. Pace, PE, welding engineer, Katy, Texas.
All right, before we get too far into this, I'm going to give you the build materials where I built this course from. So I found all this stuff floating around out there in the public domain. First one is non-destructive inspection methods, basic theory. This is a Navy/Air Force book, about 800 pages, where they just go into a deep dive into non-destructive inspection methods. I've boiled all this down into this course. Non-destructive testing, a survey. This is a NASA document, NASA SP-5113, and then the Military Handbook of Non-Destructive Testing, MIL Handbook -728-1. So this is my reference documents that I use to build this course with. So we're just I've picked and chosen. I'm not really following one of them. I've taken things that I've liked buffet style out of different courses and we put it in here. So this is where I'm going with this. So this is the build materials that I've used. This is my reference materials I've used to build this course with. Okay, so some general principles and guidelines with using NDT. One of the first ones is if we're specifying NDT, we got to make sure that there's a real need for it. We can't just fall into, well, it's always been done this way, or we did it this way the last time, or they did it, so we're going to have to do it. Everyone else is doing it. You can really run up a big bill here with just following this process. Non-destructive testing, depending on what kind you're going to do, can really rack up you can really incur some financial costs to this. So you need to know why you're doing it. And this isn't necessarily the person on the floor that needs to come up with these criteria and why we do non-destructive testing. This is more of a designer and a management and an engineering function. But we need to understand our guidelines and principles for using non-destructive testing. Sometimes NDE is specified just for administrative reasons. Sometimes the contract requires it. All right, cool. Build that into the cost. But we need to understand why we're doing non-destructive testing as an organization. So we need to determine exactly why or if NDT is required. So here's some reasons that why NDT might be desired or necessary. Increasing the production rate, by getting a higher success rate. Increase reliability, improve or maintain safety. That's a big one. To meet legal requirements. Okay, we're building a boiler. It says we have to have this much non-destructive testing on this thing so it doesn't blow sky high. To help us identify or improve process methods. All right, this process, we had some issues, this welding process when we were welding things, we had some issues, but we've done non-destructive testing. All right, we can improve our process. And to check changes in the product before they become a problem. Maybe we got a crack somewhere, or we've got some kind of flaw or discontinuity that is a defect and we need to fix it. So we need to, sometimes we need non-destructive testing to help us through these issues.
So part of the reason that companies get jammed up with NDE and they have things fail, and I say this having been there, stepped into a company when a new project was starting. Anyways, poor communication between engineering and inspection teams. We were doing way too much inspection. We didn't have a clear chain of command. We blew through the budget. They had to send somebody out from corporate to watch things. Incorrect inspection method. Maybe you should be using ultrasound and you're using x-ray, or vice versa. A lot of times this can happen. Unrealistic acceptance criteria. Maybe you're trying to find something that's way too small for the method you're using. Production pressure overriding quality concerns. Hey, we need to get this moving. And maybe corners are cut. Not that I would ever accuse anybody of that, but hey, we live in the real world. Inadequate technician training or qualification. I was on a job one time. Well, actually, I went and looked at a bunch of x-rays for a company, and they caught a bunch of stuff that should have been caught with phased array ultrasound, and the ultrasound wasn't catching it. I don't know what the problem was, but it wasn't my dance. I just pointed it out to the people that paid me to figure it out a little bit. Failure to document and track inspection results. If you don't do the paperwork and you don't keep track of paperwork and you aren't a grown-up, you're going to get jammed up at some point.
So we need to be on the same page. The production engineer might want to inspect raw materials as soon as possible, even before it arrives on site. This might be one of the reasons we want to do non-destructive testing. What kind of materials am I working with? What do I got to fix before I start producing something? Most NDT engineers, they would rather inspect the material after it has been machined, into a simple shape with smooth surfaces. That's probably how they're going to want to do it. Or, the reliability and the safety engineers want to do the NDT after all the major operations have been completed. So you can see where we've got some conflicting direction here on when different elements within any organization probably want to do non-destructive testing. So everybody needs to get onto the same page. A lot of times, all these tests, it's not affordable. You start doing a lot of ultrasonic testing or radiography. You can really incur some financial expenses, and go broke. So it's important to decide as an organization when and where in the manufacturing process NDE is going to be done, when it should be done, and where it's going to be specified. These are things that, the organization has to get on the same page.
So NDE is a cost, balance, risk, reliability mess. And it's something we need to be able to balance out, right? So more inspection is going to be higher cost, and it's going to slow production down. We can look at every weld we do with every NDE method, and it's really going to slow things down and jack the cost up. And we can go the other extreme where we don't do enough inspection and then something goes wrong and we have a catastrophic failure and things just get ugly. And this is kind of the thing we balance. And then you have critical equipment. Maybe it's something that if this thing fails, we've got the next Chernobyl in the middle of the United States. Well, we probably want to do a lot of non-destructive testing on this thing to make sure that something doesn't go wrong. And inspection timing, this is going to affect manufacturing efficiency. If I can make 3 widgets an hour, whatever these widgets are, and then it takes me 9 hours to inspect each widget, well, I can make all these widgets, but my bottleneck is going to be the inspection going on. So we need to balance this or figure out maybe there's another way that we can do this or automate it. And engineering decisions often balance economics with safety, right? We have to balance all this out. How much NDE do we need? How critical is this weld? So these are the things that we look at.
So some more reasons for specifying NDT. Everybody needs to recognize and evaluate the reasons realistically. Why are we doing this? So that those that are responsible for doing the NDE, the implementation, can give logical and effective responses to those who asked why we're doing this. So these are things we need to understand before we dive into, what is non-destructive testing, what the various processes. Odds are, if you're welding or manufacturing something, you're going to have some type of non-destructive testings. And probably the baseline is going to be visual testing, but if we've got radiography or something that's expensive, we shouldn't just automatically use it unless we have to, just due to the expense. And especially if it's all welds need to be x-rayed. Well, what if it's a handrail? Do we really need to, take the time and money to x-ray a handrail? Probably not. So, some of these costs can be avoided. So we'll talk about some of this stuff. We should always have a purpose behind the non-destructive testing that justifies its expenses. Once again, why are we using radiography on the handrail welds? Can we get away with visual and maybe a little bit of dye penetrant on these? Do they have to have nuclear level quality on our handrails? Probably not. That's probably a expense that we don't need to build into our handrails or some, non-critical weld or structural function. So one of the keys that we need to understand, one of the things we need to understand about non-destructive testing is the flaw size, limitations in flaw size. So the decision on, limitations for allowable flaw size, it's got to be made by the designer with, the production, stress, and materials engineers. How big of a flaw can we have in this part before we have problems, before things fail? That's not the guy on the shop floor's job to decide. That's the designer who's building the bridge or building the structure to say, no, this is as much porosity as we can have in this, or this is how much undercut or whatever the flaw or defect is. They're the ones that are going to tell us. They're the production, stress, and materials engineers are the ones that are going to give us the limitation on the flaw size, where they're like, nope, anything bigger than this, it's rejectable. So we need to understand that is the function of the designers and the engineers. They're the ones that are going to determine the types of flaws expected, maximum allowable flaw limits that are going to be required to achieve or maintain our design goals. How big of a flaw? Because we're never going to have anything perfect. And different codes allow different amounts of different types of flaws. There's no perfection. So these individuals and these groups need to figure this out. They're going to be the ones that determine the types of flaws expected and the maximum allowable flaw limits. So then we get to what NDT method must be used. Once they get the flaws figured out and the limitations, the NDE people, the NDT engineers, are going to respond by finding answers to more questions. And this question is, what NDT method can be used? What equipment, personnel, controls are necessary? What do we got to do? A lot of times we can't just use one method. Okay, we're just going to x-ray this and that'll get us everything we need. Well, we might want to do some visual on that, or maybe we want to do some dye penetrant, or maybe it's in our best interest. Maybe it's a ferromagnetic material. It's a steel. Maybe we want to use one of those, want to use some mag particle testing to detect flaws that might be in those materials. Whatever it is, the non-destructive testing engineers or subject matter experts are going to be the ones that answer these questions and tell us, okay, what's the most economical and effective non-destructive test method that we can use. And and we got to be able to evaluate the data. So once we've done our test, we've got to evaluate the data. And sometimes we're going to need a permanent test record. What are we going to do? Um, so sometimes, well, if we shoot x-rays, well, that's an easy one. We'll just hold on to the x-rays. Well, what are we going to do if it's dye penetrant? All right, if it's dye penetrant, we could probably take pictures with our cell phone, save it, and use that data. But, what kind of test record are we going to require? What kind of paperwork and documentation are we going to require to consider this a completed test? And once again, some NDE methods don't really have a permanent record, so we're probably going to have to figure out how we're going to have proof, documented proof, that the tests passed, and where we're going to go forward with that. So once again, it gets back to record keeping. How are we going to record keep, and what processes are we going to use? And that's the subject matter expert / non-destructive testing engineers that figure that information.
Well, and we need to understand too that no single NDE method is perfect. And I'm kind of harping on this and beating on this as we go through this course. PT, we're going to find surface stuff. MT only works on things that are magnetic, right? UT, internal discontinuities, but only in certain materials. RT, we can get a permanent image of it. And UT and RT are good for, we call those volumetric methods. And VT, visual, that's the first thing we're going to do before we do any of these others. So a lot of this non-destructive testing, this whole mantra or the belief system or the religion of it, or I don't even know if those are the right words, but the whole system boils down to knowing what I can use when, where, how, and why.
So still saying in that same vein, our general principles and guidelines for NDE are, we're going to determine exactly why NDE is required. Why are we going to do non-destructive examination? What is the purpose of this? Are we welding something up on a piece of farm equipment? Well, do we need nuclear level radiography on that? Probably not. Well, or if it's a nuclear weld where, if this weld fails, it's going to make this area uninhabitable for the next 100 decades. Yeah, we might want to, put a little extra care and really do some non-destructive evaluation on that component or that weld to make sure it's exactly what it needs to be. There's nothing that can go wrong, or very little that can go wrong. So if unreasonable, if we're looking at this and we're looking at our farm equipment and we're asking ourselves, why are we doing all this non-destructive testing on this part? Then we're probably going to want to minimize it. We did this years ago. I worked for an outfit in Iowa. They had some problems, and then they decided they were going to ultrasound every part that was welded for this one customer. Well, the prices for this part, the amount of money they were sinking into this were just skyrocketing. So I talked them into, hey man, we don't need to do this all the time. Maybe we'll do one of them. We haven't had any failures. Let's look at this from a couple different directions. So, if we can't deny the need for the NDE, well, then we need to design for inspection, because due to geometry on a lot of these non-destructive testing methods, they don't always work with really complex geometries. So if we absolutely have to do non-destructive testing, we're probably going to want to design for inspection. And then we're going to try and determine the proper place in the life cycle for performing that non-destructive testing. Airplanes get a lot of non-destructive testing. How often are we going to do non-destructive testing on this turbine or on a on a bridge? How often are we going to ultrasound the welds on a bridge to make sure they're not cracking? Or look at the bolts on a bridge, or whatever the component is. How often are we going to look at these parts with non-destructive testing to determine whether they need replacement or repair, or just need to be, the whole thing needs to be scrapped? So this is some of the guidelines that go into non-destructive testing and figuring out how often we're going to do said non-destructive testing. So, we need to establish critical flaw size and limitations. We've discussed that, okay, so how big is too big? What's the size of defect and flaw that we can live with? Okay, cracks, we don't allow cracks, but things like with some of the structural welding codes will allow a certain quantity of porosity. It's not the end of the world. Different codes have different criteria in regards to the critical flaw size. So once again, this needs to be understood. We can't have something that says no flaws allowed. Find the smallest possible flaws. These are unrealistic expectations for the non-destructive testing people. You got to give them a goal. You got to establish a critical flaw size and the limitations on that flaw size. So that needs to be done. We can't just give them a where they're searching for no flaws. It's not going to happen. You got to give them a little something more than that. So when we do tell them, when we are establishing our critical flaw size and our limitations, we should have terms such as no crack shall exceed a length of 4 millimeters in any direction, or any pores or combination of contiguous pores that equal or exceed the volume of 3 millimeter sphere shall be rejected. You want to give them something quantitative. You want to give them a target to shoot at. Something numerical, empirical, mathematical that can be measured. Once again, we don't want to use terminology like no flaws allowed or find the smallest possible flaw size. Those aren't productive in helping our NDE technicians find and disposition flaws and defects in components. And so we're going to have to determine the appropriate methods. What methods are we going to use? Equipment, personnel, what standards are we doing this to? And controls. A lot of non-destructive test methods don't reveal flaws directly, especially ultrasonic. We're going to have to do some interpretation. It's also a lot of times it's possible only through use of proper standards. How are we going to tell if this is something we need to chuck or dispose of, or we can repair it, or it's not even an issue in regards to a flaw? A lot of times indications are significant only when we can interpret them correctly. The older school ultrasonic testing, a lot of times the discontinuities that you find are it's a blip on a little screen. What am I seeing? Am I seeing a bubble? Am I seeing just some kind of crack? What have I got going on there? Is it some kind of backscatter? What's going on there? So a lot of it has to do with interpretation. A lot of times we need to use 2 inspection methods to figure out what's going on. We're going to have to use, visual inspection and mag particle, or sometimes we're going to need 2 because one method might not get us to where we need to be. Or we're using visual testing and then we see something that's a little weird, and then we use magnetic particle testing to really zero in and find out if there is a defect or a discontinuity that is actually a rejectable defect and makes that part unusable. A lot of times we need 2 methods to get a complete analysis of a part. So, and we want to establish the means for complete and proper adequate evaluations. And this, like I said, includes reports and documentation.
This is another one I'm probably going to be beating like a dead horse over the next whatever when we're doing this course is documentation and traceability really matter. Inspection results, we got to be able to repeat them. If me and my buddy Pete, he's got a crew in Butte, Montana, and I've got a crew in Portland, Maine, we should be able to do the same kind of inspections and have the same kind of reports and have them understandable. And in our reports, inspection method, acceptance criteria. Hey, what was our criteria for accepting or rejecting this weld? What code was I working to? Location of indications. Hey, we found stuff here. We need the welder to go in and chop it out and re-weld this. Who was the inspector and what was his quality level when they did this? What's our repair status, if applicable? Well, maybe that doesn't go on there, but it'll be on an adjacent report. And good documentation, it's going to support audits, code, compliance, and our repairs. If you have a good report, me as the engineer, welding engineer, I take that report and figure out how I'm going to get my guys to chop in there and fix the weld. So documentation and traceability, man, big things, really matter.
Gary A. Pace, PE, CWI, Katy, Texas, TexasWeldingEngineering.com. You got any questions, comments, thoughts, concerns? This is how you can contact me. Shoot me an email, ask questions. I generally get back to people with an answer.